In 1909 or thereabouts, Robert Millikan did several experiments to show that charge comes in natural units. Following on some earlier evidence, he was showing that there are grains of charge, and the grains are all the same size. I don't mean the same volume or the same mass, the same size in charge electrically as measured by electrical forces on them. If, for example, we have one grain of charge, it's not a dot, of course, in a given electrical situation, then there will be a certain force on it. If we have another identical grain, the same force. If there are two grains on, let's say, a small object here in the same electrical situation, the force will be twice as big. With 3 grains on an object, it would be 3 times as big. 1, 2, 3. With this kind of evidence, we can tell whether charge comes in natural units. In this film, Dr. Alfred Redfield is going to do experiments similar to Millikan's using this apparatus. On these thick metal plates, he will put charges from a battery connected to these wires. You'll see the battery and the switch later on. Plus charge on one plate, minus on the other, sometimes the other way round. That will put electric forces in here between the plates on any small charged object, any little grain of charge that we put between these plates. We'll have to put a very tiny object to carry our grains of charge in there because we want to measure the force on the smallest amount of charge that ever occurs in the world. We have to use objects so small that a microscope is necessary to see them. We get the particle in between the plates here, look at it through the microscope, and see it in light sent in from the side. This microscope will do. In the film, we'll use a somewhat better microscope to be sure to see clearly. In order to get the little particles carrying the charge into this space between the plates, we're going to use some tiny plastic spheres, shake a few into the air above this glass tube, and let a few drift down through the air, through the tube, through a hole in the bottom of the tube, into the space here between the plates. The tube has a hole in the bottom, as you see, so when they drift down the tube, a few will pass through the hole into that space. The bottom of the tube is made of metal. When it's in place here, it completes this upper metal plate, comes out flush with it across here, so that we can get a well-defined electrical situation with charge on the top plate, charge on the bottom plate, exerting forces on those few grains of charge on a little plastic sphere that we've dropped down through the air and through the hole into that space. Now here's Redfield with the apparatus. Over on the right is the microscope and the camera. In the back bit to the left is the source of light, shining in between the plates. There they are, the thick metal plates, connected through the wires on the left to the batteries. Those 4 batteries down there, and with this knob, Redfield can put in anything from 1 to 4 of them. With this switch, Redfield can connect the batteries to the plates. When the switch is in the up position, one end of the battery is connected to one plate, the other to the other. When it's in the down position, it's just reversed. And in the middle position, the battery is cut out and the plates are connected together so that there's no electrical force on a particle between the plates then. Now Redfield's putting a wire in through the hole into the space between the plates so that he can see how his microscope focuses on it. He's almost got it in focus now. There it is. Now, by using this ruler, Redfield can see how big the field of view through the microscope is. Those marks are 1 millimeter apart. Now Redfield's going to put some particles in the space between the plates. He takes them out of this water suspension on a toothbrush, particles of all different sizes. So we'll see how they behave. Sprays them in the air over the glass cylinder there, and some of them will drift down through the cylinder, through the hole, into the space between the plates. Here they come, falling down, moving at steady velocity, pulled down by gravity. Now Redfield puts some charge on the plates, and some of those particles are charged. You can see they're pulled up by the electric force. We've put the knob of the switch box on the screen over at the left, so you can see which way the plates are charged. Now, if we take the charge off, everything falls. Turn it around, some fall and some go up, but they're the other ones. Back and forth, and you'll see that there are two sets of particles charged oppositely. So when one goes up, the other is pushed down, and when the first one is shoved down, the second's pulled up. In all these shots, you'll notice that each particle moves at its own steady speed. Let's take another look at the particles as they came in, driven downward by gravity alone. When the particles are driven down by gravity, they quickly speed up, and then as they speed up, the drag of the air rapidly increases until it exerts a force equal and opposite to the gravitational force downward. When those forces are equal, the particles move constantly. This whole process of speeding up takes place so rapidly that you probably never noticed the speed-up process, even when Redfield turned on and off the electric field. But you did notice that the speeds were constant and that they were different for the different particles. All those differences arise because the particles were all different kinds, sizes, masses, as well probably as charges. We can get rid of most of those differences and get a standard behavior by using particles of a standard size and mass. When we have particles which are all the same, any differences in behavior that are left over arise solely because there are different numbers of grains of charge on the particles. So we're going to take standard particles, standard plastic spheres, 1.8 microns in diameter, that's 1.8 times 10 to the minus 6 meters, and 2.8 times 10 to the minus 14th newtons in weight. These are made for electron microscopy. Here's a picture of a few taken through an electron microscope. Here come some of the little plastic spheres now, falling down, driven by gravity. Notice that they come down at the same speed. Now Redfield is about to try to balance them by putting the right amount of charge on the plates. It's got a little too much, so they're going up. Now he's decreased the number of batteries. He's just about got them in balance. Although there are two standard spheres visible here, Redfield will keep focused on the one on the right, because Brownian motion will eventually separate them. Now we will want to be able to keep them in balance and know what balance is. So Redfield is marking the position of the knob so that we can always know exactly where we are. That position is almost exactly 3 batteries. With 3 batteries on the plates, the sphere is in balance. The amount of charge on the plates we'll call the set charge. Whenever we have the set charge, we'll know the sphere with this amount of charge on it would be in balance between the plates. By cutting the charge off the plates, removing the electric force, we can let the sphere fall. There it goes down. By putting on the set charge, we can stop it. It's in balance all over the field of view of the microscope. To keep working with it, we'll have to be able to pull it up. So Redfield is adding some extra batteries. Normally, these are not in the circuit. When the lever, the switch box, is pushed to the upper position here, the extra batteries are there, more charge is on the plates, and the sphere is pulled up. No charge on the plates, it falls. Set charge, it's in balance. Extra charge, more force, up it goes. With this technique, we can keep the particle in the field of view of the microscope while we do experiments. The experiments like the Millikan experiment that we're eventually going to do, in which we change the charge on the sphere. Let's consider for a moment how we're going to measure the added charge or the charge subtracted when we do change the charge on this sphere. Right now, the sphere is in balance. That means that the electric force upward is just equal, although in the opposite direction, from the gravitational force downward, like this. Electric force and gravitational force. Now when we change the charge on the little sphere here, there will be an additional electric force. That's the force that's going to drive the little sphere along. Suppose we add some charge and the electric force gets bigger. It gets bigger by an amount proportional to the charge, and that added force we'll call the driving force in this case. Remember, it's the added electrical force. Here it is, up this way. Now, under the influence of that force, the sphere will speed up and come to a steady velocity when the drag of the air is again in equilibrium, pulling in the other direction. That steady velocity to which the sphere comes is a measure of this added electric driving force. We know for spheres of this kind that the force driving them along results in a speed of motion just proportional to itself. We know this, but the first thing that Redfield is going to do is to check up on it. He can check up on it by allowing the sphere to fall first freely, no electric force in the region. The sphere is then driven by the gravitational force alone, and he can measure its speed. Now, to get a second known force, so we can test the proportionality of the speed to the force, he can use this electric force, the one that keeps the sphere in balance. He can do it this way. He's already got the gravitational force. He can't turn that off on the sphere. And now he takes the electric force that balances the sphere and turns it upside down and adds it on top of the gravitational force. That is the same thing as the balancing electric force. He turns that upside down, you remember, by using the switch box and taking the positive lead from the battery and the negative lead and reversing them. Because the whole electric system is turned upside down, the electric force now pushes down. In that way, he has first one force and then exactly double the force. We can now see that the speed under the one force is exactly half of the speed under two forces. Here the sphere is in balance. Redfield's going to measure how fast it falls under gravity. he'll need a grid and a watch in order to measure the speed across the grid. The grid there is the same as the one he can see. The watch will make 1 second intervals, and we'll put 1 second ticks on the soundtrack for you to hear. Now he'll drop it for 5 seconds. What about 23 on the right-hand scale across that grid in 5 seconds? Redfield will do it again so we can get an accurate measurement of the velocity. .24, just about the same. Now, in order to see that the force is proportional to the speed, we're going to need a double force to see whether we get the double speed. Redfield will put that on after he hauls the sphere up by turning the electric force, the balance force, upside down. .48 with the double force in 5 seconds, almost exactly double. You can see already that the speed and the force are proportional. Once again. Make it 48 again. So the speed doubles when the force doubles. We'll need that knowledge because we are going to keep on using the speed as a measure of the force, now that we know that the two are proportional. Now we're ready for the main experiment. With this X-ray tube, Redfield's going to change the charge on the little sphere. He's putting a shield around the tube to protect himself with an opening so that the X-rays can go right in between the plate. When they change the charge on the sphere, we'll have added charge on it, added force on it, driving it away from balance. From the speed with which it moves, we can find out the charge change. Here the sphere is, in balance. Now he's going to add X-rays, try to change the charge. It's moving. He must have changed the charge on the little sphere. You pull it up with the same charge on the plates, the set charge, with which it used to be in balance. Now he's dropping it down so that he can measure the added charge by the speed with which it'll come up. "12 divisions in the same 5 seconds. Enough charge was added on there, so with the extra electric force on it, same set charge on the plates, it came up 12 divisions in 5 seconds. Now I'll try to change it once more. He added X-rays, probably changed the charge, so he's dropping the sphere down so we can measure what the charge is. Yes, he got a change in charge, 22 divisions in 5 seconds this time, a bigger charge on the sphere. Tried changing it again, and I think he succeeded. Yes, it seems to go up faster. The amount of charge since balance has been increased, I think. And we'll measure it by hauling it up from the bottom once more with the set charge on the plates. .46, a lot more charge on it that time. Try changing it again. Not sure whether he succeeded. Yes, it seems to go slower. I think this time he knocked charge off. After he's dropped it down, we'll be able to tell how much charge there's left on there, charge difference since balance. $34. He did get some off. In a minute, he'll try changing it again. Going pretty slow. I think he knocked more charge off. Of course, it was still going up, so that there must be some added charge since balance. $13. He did get a lot of charge off. Now he's going to try changing it again. I think he didn't quite succeed, though. It seemed to speed up and slow down again. May have put some on, taken it back off again by having the X-rays too long. About 11. I think it's really the same amount of charge on there, just a different measurement of it. Have to try changing it once more. It started to fall there, did you notice? I think he knocked quite a bit off, and he could only hold it up and haul it up with the extra charge. So this time he'll have to drop it down, because he's got charge off since the balance. We'll be able to see how much came off. $12, and downwards. So he got off enough so that the added electric force on that opposite sign of charge pushed it down at 12. So Redfield can go on, changing the charge on the little sphere with X-rays, measuring what it is with a force on it, until at some time he loses it. Now here he still has it, but in that change, you see, even with the extra charge, he can't hold it anymore. It's falling down, set charge, extra charge, no matter what he does. Reverse field doesn't help. It's just gravity pulling it down there because there's no more charge on the little sphere. Well, that ends his run, and there are all his numbers, everything he measured. If you look at them, you see they're no random set of numbers. They fall in groups. Groups around 11 and 12, they're bound double it, 22, 23, triple it, around 34. So let's take a guess. Let's guess that these are all just about whole number multiples of, let's say, 11.8. Now we'll draw a graph and plot all this data in ascending order of size and compare it to spacings 11.8 apart, 1 times, 2 times, 3 times 11.8. Over on the left side, you see the downward one, a little bit over the 11.8. Then to the right of it, a point in balance. Once he got the same charge that he had to start out with. To the right of it, a group around the plus 11.8, the 11.8 upward. The next group about double it, triple it, and so on. So you see that the charge that came on and off the little sphere always came on and off in natural units. One of these units, 2, 4, 3, and so on. Never anything measured by this speed somewhere in between 11.8 and 0. Never anything but whole number multiples of a natural unit of charge. Now what about the charge that was on the little sphere when it was in balance, is that also a multiple of our fundamental unit of charge? To see that, look at this measurement, the measurement of the speed of fall of the drop under gravity. Gravity is balanced, as you see here, by our electrical force with just the set charge. So the speed of fall under gravity is a measurement of that electrical force and a measurement of the charge on there. So these measurements, measuring the charge through the speed of fall at 23 or 24, show that there are just two natural units of charge on the sphere. Just two of the natural units when we started out with the sphere in balance. From these experiments, we should take away two kinds of knowledge, some specific numerical facts and a general conclusion. Let's go to the numerical facts first. When we put charge on these plates, which are almost exactly 3.1 millimeters apart, we were able to balance one of our standard spheres between the plates with two elementary charges on it. We put the charge on these plates from these batteries with the knob here, which selected out 3 batteries. In fact, we could just as well use 3 of these batteries connected in series, then connected to the plates. Then we can actually find out that these 3 batteries do put one of the spheres with 2 elementary charges on it in balance. The sphere weighs 2.8 times 10 to the minus 14th newtons. So the electrical force up must be that big on 2 elementary charges. The electrical force from 3 batteries putting the charges on the plates is therefore just 1.4 times 10 to the minus 14th newtons on any elementary charge between the plates. These numerical results will be useful to us later. But it's far more important to look at the general conclusion. From this whole set of experiments in which we put charge on, took charge off, shooting X-rays at the little sphere, what we found out was that there are elementary units of charge, that nature provides grains of charge all the same size, so that we always saw 1 or 2 or 3 of these grains or some other whole number through the forces. That's the really important conclusion. The existence of a natural unit of charge in which all charges come.
Earlier in this course, we found that matter comes in atoms and that currents come in electrons. Now, what about light? Are there light particles? Well, I'm going to show you an experiment which proves that there are. Now, you remember that we didn't see the effect of electrons till we had very weak currents, nor did we see the effect of atoms until we had small amounts of matter. And we're going to have to use very weak light in order to see the effect of the light particles. Now, how do we study light? We can use a photoelectric cell. Here is one. It consists of a metal plate in an evacuated envelope. And when light strikes this plate here, electrons are emitted, and they're collected by this little electrode in here. And the amount of current is proportional to the amount of light striking the tube. And if you have very dim light, you don't get much current, so you need an amplifier. Now, we can use a photomultiplier, which is a photoelectric cell with an amplifier built into the same bulb. Now, you can't see how it works here, but I can show you on the blackboard. It consists of a number of plates, something like this. And the light comes in and strikes the first one, and some electrons are emitted. Here's one, for instance. It's attracted to this plate by a voltage of perhaps 100 volts applied to it, and when it strikes the plate, it knocks out 4 or 5 electrons, and they're attracted to the next plate, something like this. And each of the electrons that strike this plate, in turn, knock out 4 or 5 electrons, and they are attracted to the next plate, and so on. And eventually you get a pretty heavy current, and you can collect it after you've had enough multiplication. And with a tube such as we have here, with 9 stages, the multiplication is about 1 million. To check that, we can use our sensitive ammeter first to measure the current going into the first stage, and then to measure the full output at the collector here. That current should be 1 million times greater than this one. Let's do it. I have here a sensitive ammeter, which I can use to measure the current going into the first stage of the multiplier. Let me put the tube out where it gets some light. And you see I have a reading. And when I keep the light from going into the tube with my hand, the reading goes away. Now that's much too much light to use with a sensitive device like a photomultiplier. So let me turn off some lights. Now let's see what our reading is. It's 5 times 10 to the minus 11th amperes going into the first stage of the multiplier. Now we will read the full output of the multiplier. So let me connect it up. And with the same amount of light, I find that I have to go down 1, 2, 3, 4, 5, 6 powers of 10 to get about the same reading. So we conclude that the amplification is about 1 million, as we said. Now let's put the output of the photomultiplier on the cathode ray oscilloscope. And now I'll cover it with my hand, and then take my hand off suddenly, letting the light in. There, it responds. I'll do it again. Now I'd like to use weaker light, and I guess I'd better connect in this little amplifier. And you see there are pulses. Now we have weak light, and we see pulses. Does this mean that light comes in particles? Well, not necessarily, because remember how this works. Light comes in, and it makes electrons come out of the first plate, and they're amplified in here. And then you see it on the scope. And so naturally you see pulses. We know that electrons are particles. We have to do some other kind of experiment to prove our point. Now, there's another effect of photomultipliers that I want to show you, and that is that even when I exclude all the light by covering it with a black cloth, you still see some pulses. not of many. And this background is an effect that is common to every kind of physics experiment. Fortunately, we can get rid of most of it by cooling the photomultiplier. And I'm going to do this with dry ice and alcohol. Let me put the tube in this box. Put in some dry ice and some alcohol, and that will cool it nicely. Now I've described to you our apparatus. What sort of experiment are we going to do? Well, let me explain it to you with an illustration. I'm going to assume that you're very fond of milk, and that you have to have a quart of milk once a minute. And I'm going to supply it to you in a rather strange way. Behind this wall is a vast amount of milk, capable of flowing at the rate of 1 quart every 10 seconds. And once a minute, this gate opens for 10 seconds. So the milk starts flowing out, and at the end of 10 seconds, you have your quart. In this case, the milk is packaged in quart cartons, distributed along this conveyor belt in an arbitrary way, such that 1 quart goes by any point, on the average, every 10 seconds. This gate opens once a minute for 10 seconds, just as this one did. Now, is there any way that you can tell whether the milk is in bulk or packaged just by what happens down here? Not by looking through the gate or by looking for cartons or anything like that. Certainly. All we have to do is watch. When the gate opens, the milk starts flowing in this case, and it takes a full 10 seconds to get a full quart. But in this case, when the gate opens, a quart might come through right away, or 2 quarts, or 3 quarts, or none at all. On the average, of course, you'd get a quart every time the gate is opened. Now, you don't know either when the quart will come through during the 10-second open time. It might come through right at the start or at the end. Here there is no consistent delay in the arrival of your milk. But here you must always wait for 10 seconds after the gate is open before you have your full quart. This is the idea that we are going to use to find out whether light is packaged or in bulk. Here's our light source. And here is a shutter which plays the same part in our experiment as the gate did in our illustration. It consists of a disc with a hole in it. And every time the disc goes around, this hole lines up with a hole in this plate and lets light through. The disc is driven by an electric motor that you see here. Here's a drawing of the apparatus. Here's the light source, the shutter, and the photomultiplier. Light will reach the photomultiplier only when the holes in the shutter line up. This will happen for a brief instant during each revolution of the disc. What we're going to do is look for a delay in the emission of photoelectrons after the light strikes the photomultiplier. Now let me line up the whole apparatus. And I will use our ammeter to tell me when light gets through. I'm turning the motor shaft so that the holes line up and light gets through. Now the meter reading is maximum. I'll shut the light off with my hand. Now that's a pretty strong light, and I want to reduce the intensity so that, first let me put on this shield, which will keep stray light out. And now I'm going to use these filters, which reduce the light intensity by a factor of 100. Let me put one in. The reading now is 3 times 10 to the minus 4th amps. I'll put it in. And now I get 4 times 10 to the minus 6th amps, a factor of 100. Let me put in another. That's about 5 times 10 to the minus 8th amps. Again, a factor of 100. And now I'll put in a third. Well, now I have to use so much sensitivity that the meter reading isn't very steady, but it's about 3 times 10 to the minus 10th amperes. Now that's the current coming out of the photomultiplier when there are 3 filters between it and the light. But look, this is the output of the photomultiplier. 3 times 10 to the minus 10th amperes. What is the input? That's this current produced by the light. And we figured out that this device had an amplification of 1,000,000. So that current must be 1,000,000 times smaller, or 3 times 10 to the minus 16th amps. Now we can express that current in terms of the number of electrons per second. It's about 2,000 electrons per second. Which means, on the average, 1 electron every 2,000th of a second. 1 electron per 2,000th of a second. Now, this is just the same sort of statement as 1 quart of milk every 10 seconds. Now, when the milk came in bulk, we always had to wait a full 10 seconds after the gate opened before we had our quart. And if light comes in bulk, we'll have to wait a 2,000th of a second at this intensity before we get an electron. Now, if the milk was in packages, we would sometimes get a quart right away when the gate opened. And if the light is in packages, we may sometimes get an electron the instant the shutter opens. Now let's do our experiment. I'll turn on this motor, which spins the shutter at 60 revolutions a second and lets the light through for a brief instant 60 times a second. Now I'll connect the photomultiplier to the cathode ray oscilloscope. And so we can see what we're doing, I'll take out these 3 filters. Here's where the shutter is open. Now, you notice that I've synchronized the sweep of the cathode ray oscilloscope with the rotation of the disk, so that the on period always takes place at the same point. How long is that on period? Well, I can measure it with the cathode ray oscilloscope, or I can figure it out from the geometry of the disk. It's about a 5,000th of a second. Now let's expand the sweep. And now you see the pulse more clearly. Let me mark the start and finish of it. From here to here is a 5,000th of a second. Now I'm going to put in a filter that reduces the light intensity by a factor of 100. I'll need more amplification. And you can begin to see the effect of the electrons. Let me put in the second filter. More amplification. And now you can distinguish individual pulses. Notice also that there are some pulses outside the on period. This is the background. It has been greatly reduced by the cooling of the photomultiplier. Now I'll put in our third filter. The light intensity will then be so low that we'll only get 1 electron every 2,000th of a second on the average. But look, This is a 5,000th of a second from here to here. A 2,000th of a second from the time the shutter opens is out here, well after the shutter is closed again. If we had to wait a 2,000th of a second before getting any electrons, that is, if light comes in bulk, then we couldn't get any electrons at all because the shutter is no longer open. But we do get them. We not only get them in less than a 5,000th of a second, but in fact almost when the shutter opens. Let's stop the film and look at a pulse that occurred right after the shutter opened. I measured this one and found that it occurred 6 microseconds after the shutter began to open. Here's another with a delay of roughly 6 microseconds. We see pulses within times that are small compared to a 2,000th of a second. Now, what does this mean? It means that light does not deliver its energy in a continuous stream, but in particles. Remember our illustration. When the milk was in bulk, it always took 10 seconds after the gate opened before you got your quart of milk. If light is in bulk, we would expect 1/2,000th of a second delay between the opening of the shutter and getting any electrons. Experiments like this and many others have convinced us that this is the right interpretation. But these particles, called photons, are not the same kind of particle that Newton talked about. For one thing, they're intimately connected with waves. We're going to show you experiments in which you will recognize the photon, and at the same time, you will see wave phenomena. Waves and particles, we need both concepts to describe the behavior of light.
We are about to start the study of Newtonian mechanics, the science of mechanics as developed by Sir Isaac Newton. This science of mechanics is a first-class method for calculating how forces affect the motions of bodies. Now, when I say it's a first-class method, I mean something pretty simple. That for bodies as small as left, and then a shadow, or for motion as slow as the blossoming of a flower, or as fast as the alpha particles that make these cloud chamber tracks. We can calculate for all of that what a force does to change the state of motion of a body. If we were being a little stuffier than usual, we might want to begin with the definition of a force. We might use the one that Newton wrote in his Principia. He wrote, "An impressed force is an action exerted upon a body in order to change its state, either of rest or of moving uniformly forward in a right line." Now, that's a good scholarly definition. But ever since your early childhood, you've had good, sound notions, good intuitive notions of what a force can do. Sometimes pairs of forces can be used to stretch or to bend something, and when released, allow it to go back. Sometimes pairs of forces can bend it until it breaks. Or sometimes a force accelerates a body and speeds it up. Sometimes a force accelerates a body, changing the direction of its motion. Sometimes a force accelerates a body and slows it down. What I'm saying is that your intuitive notions about force are as good as those of any professional physicist who's worked with these forces all of his life. And the reason for this is simple enough. You've worked with forces all of your life, too. But there are a couple of ways in which I think your notions about force may differ a little from mine. In particular, you think about forces as coming about by virtue of contact. That this tennis ball makes contact with the racket. That this demolition ball brought this building down by contact. That they are making contact when they block and tackle. Now you think of that as contact between two bodies. That body A pushes on body B, something touches. But by the time this course is over, you're going to discover that the notion of contact, the notion of touching, is a very peculiar one. That actually, when body A pushes on body B, there's some space between with no intermediary. That body A is here and body B is there, and it pushes or pulls on it at a distance. Now there's another idea. You probably believe that there is a tremendous variety of forces in nature. The force of gravity. The force of pressure in a gas. The forces that keep this airplane in the air. The forces of the wind. The minute forces of surface tension that hold this water drop together. The magnetic forces that make the wheels of industry go round. The point I want to make is that with all of these forces, there are only three fundamental different kinds. That any force is one form or another of these three fundamental types. Now, the fundamental types are the following. First, a force of gravity. Two, the electrical forces. And three, and last but not least, the forces within the atomic nucleus. We'll call those the nuclear force. Now, to be sure, these forces differ from each other in a great many ways. But there's one thing they share in common, and that is that all of them depend upon the distance between the bodies that are involved. Let's study, first of all, let's talk about the force of gravity. It's a powerful force, and everybody here thinks it must be tremendous. After all, it holds the universe together and keeps the Earth going around in its orbit. But what about the force of gravity between two ordinary things? The way to look at that is to try an experiment. Let's go do it. Before we go to the actual apparatus, let's take a look at what we're going to work with. Here are two bottles of water, yardstick. This is supported by some tape recorder tape. You may remember that a torsion pendulum is the most sensitive apparatus that the physicist has. In this one in particular, all you have to do is blow on one side, and away she goes. Now let's take a look at the apparatus that we're going to use. We've moved over into a garage to get away from the hustle and bustle of the studio. We're going to repeat an experiment performed by Cavendish more than 100 years ago. We're going to try to measure the force of gravity between a box of sand and a bottle of water. You could repeat this experiment yourself if you wanted to. It's not too difficult. But instead of using just one bottle, we have 2 bottles of water and 2 boxes of sand. Our 2 bottles of water are suspended from a yardstick that you can see. The yardstick, in turn, is suspended by means of some recording tape, thin recording tape that goes clear to the ceiling. The period of oscillation of this torsion pendulum is pretty slow, about 10 minutes. So what we're going to do is to show you the oscillation of it in stop frame photography at a rate of about 60 times normal. In order to show the angle of twist of the pendulum, we have a mirror attached to it right down here. A light spot is reflected from it, shows it swing on the wall. The period of the pendulum is really 12 minutes, but you see it here in 12 seconds, as the minute hand of that clock shows. And I'll mark the middle of the swing, like that. Now we're ready to put the boxes of sand in place so that they can pull on the bottles. Okay, now we're ready to watch the sand pull on the bottles. It's swinging. And the center of swings is displaced over to one side. And I'll mark a new center of swings. Now, instead of setting the boxes back the way they were originally, what I'll do is to move them around so that they deflect the pendulum in the opposite direction. This will give me twice as big an effect. There it goes. Now it swings over to the other side. And there you've seen the effect of the force of gravity acting between relatively small bodies. Question is this a powerful force? You know that it doesn't take much to twist a piece of recorder tape, especially if it goes all the way from the floor to the ceiling. But it's common to think of gravity as a large force. But you remember that the mass of the Earth that pulls on you is a lot bigger than the mass of that box of sand. Notice another thing. Notice, too, that the glass and the screen wire had no effect. But the screen wire is there for a reason. Watch this experiment. I can charge this lucite rod up here by rubbing it on my sleeve and pick up a piece of paper very easily. Let's see if that charge, which you proved to be there, see whether that has any effect. None at all. Screen wire shields it out. But let's see what happens now if I very gently lower the case and hold up this charged rod. Practically jumps out of the case. Look at that. The electric force is tremendous compared with the gravitational force. We'd better go back to the studio and look at that electrical force a little bit more. You just saw this electrified rod pull on a bottle of water, just as it does on this ping pong ball. But there's one big difference. I can rub this off. And you can't do that with gravity. Well, one more thing. The force depends on the distance. Watch. Closer I get, the harder it pulls. And one more. Suppose I let it touch. Then it'll repel. And you never saw gravity repel. And still another. This electric force will work on everything. Here are a couple of samples. Here's another one. Now let's try one peculiar one here. It's a piece of dry ice. Now, just like the force of gravity, the electrical forces act through a vacuum. Let's go look. Here's an apparatus you think you saw in a film on the pressure of light. Remember, there was a piece of aluminum foil suspended from a quartz fiber in a very well evacuated vessel. But this was an early version before we'd caught on to the fact that we had to do very careful screening of the electrostatic forces. Let's see what the electrostatic force really does. Watch this. Now you see the electrical force pushing through glass, vacuum, and all. Let's take a look at this tube over here. It looks familiar. It's a cathode ray tube. You've seen plenty with television pictures on them. There's a stream of electrons starts here at the gun and goes up to the face of the tube. The reason it's antique is very simple. The manufacturers hadn't then caught on to the fact that they had to screen their stream of electrons from external electric forces, just as we had to in the Cavendish experiment, just as we had to in that pressure of light experiment. But let's see that behave. Let's see what happens. I bring in a charged rod, and the spot moves down. That means we're pushing down on the electrons, and the electrons hit at a lower spot on the tube. You know, we almost forgot about the magnetic forces. Not really. Here's a magnet. Now let's bring it up near to the electron stream. Here we go. Notice, though, that when I bring the magnet down from the top, the spot moves off to the side. And when I turn the magnet over, the spot moves toward the side, but toward me this time. Whereas, with the electrified rod, when I bring it down from the top, the spot moves away. Now, you're going to learn later in the course that the magnetic force depends on the motion of the electric charges, not just on the charge. But one more thing. When the magnet is far away, the force is small. And when I bring it up closer, the force is large. In order to summarize, let's consider these two apples. The gravitational force between them at large distance is trivial. If I put them together, the gravitational force is still nothing to write home about. And the reason for that is simple enough. Neither apple is large enough, like the Earth, to make a large gravitational force. When the apples are close together, when the apples are touching, then the atoms of this apple are very close to the atoms of that apple, only a few atomic diameters away. We put them that close together, the electrical forces are huge. And we try to squeeze them together further, the electrical forces go up very, very rapidly. And that's what we meant by contact earlier in the film. We said contact was a peculiar notion, and we meant simply that you think of something as touching, whereas actually it's only that the electrical forces increase very rapidly when you try to put these two things closer and closer together. Now, we haven't said much about the nuclear forces, and indeed I'm not going to say much about them either, except this. Suppose we let the two apples represent two atoms. Then when the atoms are close together, as they are here, and the nuclei that are way inside the atoms are here where the seeds of these apples are, then the nuclei are far apart. So that in this circumstance, the nuclear forces are trivial because for them, they're too far apart. They're buffered by the electrons that are around them that go to make up the bulk of the atom. Under some circumstances, however, when the nuclei get close together, or when nuclear particles get close together, and under special circumstances, the forces are clearly very big, and I mean really big. It might seem sensible to you for us to cut this film here. After all, we've talked about all of physics and all of chemistry and probably all of the other sciences too, at least the forces that underlie all of these sciences. But we're not going to do it. A professional scientist always starts to study something complicated by studying something simple first. That's what we do. And let's take a simple case. It may look trivial to you, but let's look at it. Here are two bodies, and I make a collision. Body A collides with body B. That's already too complicated. There are two bodies and two motions to study. Let's anchor that one, like that, and make a collision, and study the motion of this one. I want to go one step further. I want to hide this body. I want to hide the source of the force and study the behavior of that body under the action of one force. That's the way we're going to start the study of Newtonian mechanics. Just that way.
Today we're going to talk about the motion of bodies along curved paths. And we're going to try to answer these questions. What kind of forces make bodies move along curves? And what is the relation between these forces and the curves which the bodies follow? Let's take a look at a typical example of motion in a curve. It's a picture of an athlete getting ready to throw a weight. You see him whirling the weight around his head. It speeds up, and finally he lets it go. Now, the forces which act in this motion are really complex because by far the greater force is exerted by the man, by his muscles, and these are very difficult, if not virtually impossible, to measure directly. Besides that, of course, we have the gravitational pull of the Earth. Rather than try to analyze such a complicated motion, however, let's turn to a simple one that we've met. If I throw this ball in this fashion, it traces out a curve which is sketched on the blackboard. Now let's take a look at this again in slow motion so you can see the detail. In this case, we know the curve, and we're sure we know the force, the only force that acts on this ball after it leaves my hands. This is its weight. At any point of the curve, we can indicate the direction of motion. That's the velocity vector. And the net force which acts on the body, in this case, vertically down. Now, the difference between this curved motion and straight line motion lies in the fact that the force is not in the direction of motion. There is a component of this force at right angles to the motion, and this does not appear in motion in a straight line. This is the direction at right angles, and the component of force along that line is responsible for the motion in a curve rather than in a straight line. It deflects the body from straight line motion into curved motion, and we shall call it a deflecting force. Now, what else does a deflecting force do besides producing the curve? Does it, for example, affect the speed of a body? Such a question can only be answered by looking at an experiment. And let's do one to investigate this particular situation. Over here, we have a frictionless disc with a string and this little rubber loop. Now, I can exert a force on this disc by pulling the string. The loop will stretch, and it will stretch farther the larger the force I exert. My experiment consists of starting this puck without any force on it. It'll move in a straight line, pulling on it and adjusting the pull to always be at right angles to the motion, and then stopping. Let's watch it. There's the straight line part. Now I pull, keeping the pull at right angles. Now I stop. Now let's do it once again, and this time I will change the strength of the pull, but do the experiment exactly the same otherwise. Here we go. The straight line part, the sharp pull, the last straight line part. Now let's do this over again, and I want you to notice the difference in the kind of curved motion that occurs when I pull with different strengths. Here we go with a gentle force. There's the straight line portion. Now I pull gently, always at right angles. There's the remaining straight line portion. One final try using a larger force. And remember, the trick here is to keep pulling at right angles to the direction in which it's moving at every instant. The thing to notice is that where I exerted a larger force, the curve was more sharply bent than in the first case. When the force was small, the curving was relatively small also. We've taken a series of flash photographs of motions just like the ones you've looked at and mounted them over here on this easel where you can look at them. First, look at them as a whole and focus your attention on the centers of these pictures of the moving discs. You see how equally spaced they are all along both motions, indicating that the speed is constant everywhere. If we look at the string and the little ring, we see in this straight line portion there is no force. Here you see a force, rather small. Here a larger force, a larger stretch, always at right angles to the motion. Similarly in this picture, no force, a strong force at right angles, an even bigger pull here, and finally no force again. We can check the constancy of speed in the straight line portions very easily by using a pair of dividers so. There is the separation of two successive pictures in 1/2 a second. At the end of the motion, you see the separation for the same time interval is the same. Now in the other case of this sharply bent curve, we have exactly the same situation. There is the separation between successive pictures. It stays constant. Over at the end of the motion, you see the same separation. We conclude that a pure deflecting force can change only the direction of motion of a moving body, but not its speed. We now ask the question, what kind of curve will a given deflecting force produce when it acts on a moving body? In general, this is a complicated question. So we will look at the simple case of a deflecting force of constant magnitude. You remember in these pictures that a relatively small force produced a gentle bending of the curve, and a relatively large force produced a sharp bending. A constant pull must produce a curve which is uniformly and equally bent everywhere. What do I mean by a curve that is bent uniformly and equally at every point? Over here, I have a piece of such a curve which bends steadily. If I turn it around, it looks exactly the same. And if I were to cut it in halves, or in thirds, or in quarters, each piece would have to look exactly like every other piece. Now, instead of trying to cut this piece, I have already taken identical pieces which are cut. You see it's identical with the original. Each piece is identical with the other. Let me show you what happens when we cut it in 3 pieces. This hole is identical with our original arc. When I put these 3 pieces, one on top of the other, they all line up. If I turn one over, they still line up. Therefore, we have shown that this piece of curve is uniformly bent. Now, to find out just what sort of curve a moving body will follow when it's pulled on by a constant deflecting force, I will use this series of identical arcs, each one just like the one we've already used. Since the body moves with constant speed, each of these represents the same interval of time. Let's take it as 1 second. Imagine the body starts here on the outside edge of this one. At the end of 1 second, it will have moved from here around to here. In the next second, it must move along an identical arc. Here it is, and move the same distance. So it gets to here at the end of 2 seconds. At the end of 3 seconds, it moves from here to here. You probably see by now the sort of curve that is going to result. At the end of 4 seconds, we're here. At the end of 5 seconds, we're here, and now it's pretty clear what's going to happen. There's the next second's travel, and the next one. And you see that a circular path has evolved from the action of a constant deflecting force acting on a body which is moving with a definite speed. Now, a circle is a curve which looks everywhere the same. At a constant pull at right angles to a moving body will make it move in a circle. While I hope it's convincing, I'm sure that there are some among you who may wonder a little, does this really happen in motions in nature? To find this out, let's do an experiment with real circular motion. Here's a frictionless disc, a little ring to indicate force, and in this case, we have a string which is attached to a fixed post on the table. Now let me start this. So, and adjust that. And there you see circular motion. It will be a circle if the stretch of the rubber ring is constant. But a constant stretch of that ring also means a constant force. Now, in order to make sure that ring has been stretched the same amount at all points of the motion, let's take a look at a picture of this circular motion. Here are a series of flash photographs taken at 1 second intervals, and on it we can check the constancy of stretch of the loop, which indicates the magnitude of the force. You see, it's the same at every point. Therefore, we have established that a constant deflecting force will cause a body to move in a circle with constant speed. But how big is the circle for a given size force? To answer this last question, we must have a relation between the force and the radius of the circle. Now, what we know from our past studies is that the relation between force and motion for straight line motion is given by Newton's law. F equals ma. And we also learned when we studied the motion of projectiles that this law held in vector form. Vector force equals mass times vector acceleration for that projectile motion. If this vector law is true for motions other than projectiles, such as our circular motion, then our problem becomes to calculate the acceleration A in terms of the radius of the circle and the speed with which the body moves around it. How do we calculate this acceleration in terms of speed and radius? Come with me and I'll show you how. Here's a body which can rotate uniformly in a circle, as you see. We'll locate this body by fixing a reference point at the center of the circle, constructing a vector with its tail at the reference point and its tip at the body. This is the position vector, and you notice that this position vector has a length just equal to the radius of the circle in which the body rotates. I will label it capital R. Now, as the body rotates, it moves with a definite velocity, and this velocity is directed tangent to the circle. So, that is, at right angles to the radius vector. Let me label this velocity vector V. Now, as the body rotates, it moves along the circumference of a circle, and the length of this circumference is 2 pi r. If the time it takes to move this distance is capital T, the period of the motion, then the speed, the magnitude of this vector, must just equal 2 pi r over the period T. Here it is in writing. Now notice as this body moves in the circle, the position vector rotates uniformly, and this velocity vector is then the rate of change of a uniformly rotating vector. But now, the velocity vector itself rotates uniformly just as the radius vector. It's easy to see that the radius vector rotates uniformly, but it's not so easy to see that the velocity vector rotates uniformly. The reason is that the end of the velocity vector keeps moving in a circle, whereas the end of the position vector is fixed at the center of the circle. But to make it somewhat easier to see that the velocity vector in fact does rotate uniformly, let's take another vector of equal length and place it with its end at the center of the circle, adjusted so that it is parallel to the velocity vector. This vector, which is the image of the velocity vector, will reproduce every direction in which the velocity vector points. Let's rotate the disk now and watch what happens to this image vector. You see it rotates uniformly just as the position vector does. Now, if we wish to calculate the rate of change of this rotating vector, this image vector, we do so by the same argument by which we calculate the rate of change of this rotating vector. The rate of change of this is 2 pi times its length divided by the time of one revolution. But the rate of change of this image vector is identical with the rate of change of the velocity vector. And remember, rate of change of velocity vector is acceleration. That's what the word means. So we have calculated the acceleration, its magnitude, as equal to 2 pi times the speed divided by the period. Here this is in writing. Now how about the direction? Well, for this purpose we can dispense with our image vector and take a look at the relation between the velocity and the position vector. The velocity vector is at right angles to the position vector. Since this is the rate of change of that, the acceleration vector must be at right angles to v. There it is, let's say. But this is an awkward representation because the acceleration vector hangs out here in empty space, so to speak, whereas it really refers to the acceleration of this body which moves in the circle. So let's put an identical vector with its tail at the body whose acceleration it represents. There you see it. We remove our construction vector, and you see the acceleration vector points toward the center of the circle. Well, that completes the analysis, and the rest is a little arithmetic. If we eliminate between these two equations the velocity and express the acceleration in terms of things that you measure directly, distance, the radius of the circle, time, the period of rotation, this is the result. The acceleration is 4 pi squared times the radius of the circle divided by the square of the period. This should hit you right in the eye. Meters per second squared. That's what an acceleration is expressed in. Now, it's more usual to express this acceleration of a body moving uniformly in a circle by the following relation. V squared over r, which you can obtain from these two equations by eliminating the time. Now that we've derived this expression, let's go back to our flash photograph. If we measure the radius of the circle, r, and we do this by using the scale on the side, and the period of the motion, capital T, which we can do by counting the number of images appearing in one complete circle, remember they're 1 second apart, we can substitute these values in this formula and calculate the numerical value of the acceleration. I have this on a card radius 36 centimeters, period 15, and the acceleration comes out 6.3 centimeters per second per second. Now we ask the question, what would happen if we applied the same force to the same disk, but let the disk start from rest? We wish to know whether the acceleration in straight line motion is the same or different from the one we have just measured. Now, Professor Purcell has performed this experiment, and you've seen it. He used the same disk. He used the same rubber ring, stretched the same amount. Actually, we picked out of all our tries that experiment in which this rubber ring was stretched as nearly as we could tell, the same amount as in the Purcell experiment. Let's find out what value of acceleration he established for straight line motion.
That distance is 24.8 centimeters. So the average speed in this 1 second was 24.8 centimeters per second. Now we'll treat the next interval just the same way. Measuring off the distance traveled in 1 second. Let's compare it to the scale again. 30.9. So now the average speed in this interval is 30.9 centimeters per second. The increase in speed from 1 second to the next was 6.1 centimeters per second, the difference of these two. And that, since it occurred in 1 second, is the same as the acceleration. In this run, then, the acceleration was 6.1 centimeters per second per second.
This acceleration of 6.1 centimeters per second checks the one which we found with an experimental error. It takes just as real and hard a shove to deflect a body out of a straight line motion as it does to speed it up in a straight line motion. We must ask, what have we learned by this equality of acceleration for two widely different motions? We've learned this. First, for straight line motion, when a force acts on a body in the direction in which it's moving, or opposite to it, we know that Newton's second law holds. In the case of projectiles, we studied the motion under the action of a force constant in magnitude and in direction, but the motion wasn't necessarily in the direction of the force. There we got our first evidence that Newton's law in this vector form was true. Now, in this motion, we have something new. This is motion under the action of a force which, although constant in magnitude, keeps changing direction. So you see, the validity of this vector law seems to grow every time we try a new experiment. Now, countless thousands of experiments of all sorts have verified the validity of this law. And at this stage, we're going to say we accept Newton's law in its vector form as one of the great principles of physics. Having done this, we really have in our hands a powerful tool to investigate forces in nature which otherwise are not apparent. Let me show you what I mean by going back to our circular motion. Here is an experiment which you may think you've already seen. Our frictionless disc, the string, the center post, and there you see the circular motion. But one thing is missing in this motion compared to the previous one. The little ring that indicated the force acting is missing. All we have is an inextensible string running from the center post to the moving body. That tells us that the body moves in a circle, but it certainly hides every evidence of a force. How do you know that this string is pulling on the moving disc? By looking at it, you certainly don't know. Here's where we make use of Newton's law of motion. From the speed of this moving body and the radius of the circle in which it moves, we can calculate the acceleration. And once the mass has been determined, we can predict precisely what the force must be with which this string pulls on the moving disk. Now, you know there are many motions in nature in which you haven't even got a string to make you suspect there's a force. But by studying the motions, you can be sure that such forces must actually exist. Look at the moon, for example. Here's a body that moves in a circular path around the Earth, practically a circle. It moves around with a period of 28 days, roughly. Uniform motion in a circle. From the motion, we know the acceleration is constant in magnitude and points directly toward the Earth from the moon. Therefore, there must be a force exerted on this moving moon which is directed toward the Earth. It was by using considerations such as these that Sir Isaac Newton, as you will learn in detail in a few weeks, was led a long way in his uncovering of the universal law of gravitation. I'd like to tell you about one more example that nature gives us of a deflecting force of utmost importance, in which we haven't got any strings, no physical evidence other than motions that such forces exist. These are magnetic forces. You've already seen a magnetic force in a film by Professor Zacharias, the one on forces. A magnet exerts deflecting forces on a stream of moving electrons. Such a beam of electrons you see in this film. Here, the stream of electrons moves through a gas, and the collisions of these electrons with the gas molecules forms a track of light, which you see as the path of this beam. Here in a uniform magnetic field, you see the track. It's a circle. This means that with this experimental arrangement, the deflecting force is constant in magnitude. And if I increase the magnetic field, the force increases, and there's a smaller, tighter circle. Although the laws which we've developed today are more than 200 years old, they are by no means obsolete. Now let me summarize very briefly for you where we've been today. We've asked what sort of forces make bodies move along curves. We found that forces which push or pull at right angles to the motion of a moving body cause the body to move in curved paths. These forces do not affect the speed. We further found that when such a deflecting force is constant in magnitude, it makes a body move in a circle. We used this evidence to build up our faith in the generality of Newton's vector law of motion. And then we indicated how this law can be used to uncover the nature of forces by studying the motions they produce. And this is invaluable in those cases where there is no other evidence for the existence of such forces.